Hey there, in this video we're going to cover section 6.6, which is normal approximation to the binomial. And we're going to start with this problem that you may have already seen if you took the survey. So the background is that in a study conducted by Psychonomic Bulletin and Review, they presented evidence that people use facial prototypes when they encounter different names. Participants were given two faces and had to choose which one was Bob and which was Tim. The researchers wrote that their participants overwhelmingly agreed on which face belonged to Bob and which face belonged to Tim, but they did not provide the exact results of the study. And by the way, the men in these pictures are not real people. In the first of two studies reported in the paper, different people were given a computer and software to allow them to create faces, and the task was to create a face for someone named Tim and to create a face for someone named Bob. And then these pictures were created based on those other pictures. So someone took all of those pictures and created a composite of what a Tim looked like based on all those pictures and what a Bob looked like based on all those pictures. So that's what these pictures are. So these are not real people. So in the class survey, I asked you to choose the name of the man in the image on the left. And so just to collect my data without any bias, there were different options. Some of you were asked to choose between Tim or Bob, and others were given the option Bob or Tim. So I switched the order in which the name was provided, so in a way to try to eliminate any potential bias. All right, so we're going to go through the 6-step process of doing statistical analysis. Step 1, ask a research question. Step 2, design a study and collect data. Step 3, then explore the data. Step 4, draw inferences beyond the data, and then that's the longest one. Then step 5, formulate conclusions, and step 6, look back and ahead. So let's go back to the beginning. So identify the research question. So in this case is, do STAT 300 students use facial prototypes when they encounter different names? And the reason for this particular question is because notice that here there's no particular data given. There are no results of a study, right? It actually says that they did not provide the exact results of the study. So the data that we're going to analyze is the data from the survey that I created. So what was my survey? My survey was intended for STAT 300 students. So that's why the research question is not, do people use facial prototyping, but it is instead, do STAT 300 students use facial prototypes, because that's the data that I collected was from STAT 300 students. So what are the observational units? Moving on to step 2, design a study and collect data. Once we have a research question, then how are we going to collect the data? So who or what are our observational units? And so we can say the observational units are STAT 300 students, because that's who we are asking information from. What is the variable that is being measured and recorded on each observational unit? So what is the question? What am I keeping track of? So we are keeping track of the name that was assigned to the image on the left. And then what type of variable is this? Is it categorical or is it quantitative? And so think about the responses. So what were the options? You could either assign Tim or Bob, right? Or Bob or Tim, whichever option you get. So, but either way, there are two options. We can say it's categorical. And because there are only two options, we can also say that is binary. So this kind of fits with the binomial distribution, right? Because then you're going to have success and a failure. And so we're going to keep track of that. Describe in words a parameter of interest in this study. Now remember, parameter refers to the population. And so, and a statistic refers to the sample. So let me write that down real quick. So then describing what's the parameter in the study. The parameter in the study then will be the proportion of all STAT 300 students who do what? What is it that I conjecture? Let's go back up to the top. So I said I conjecture that students are more likely to assign the name Tim to the image on the left. And so that would be the parameter then that will be the proportion of all STAT 300 students who assign the name Tim to the image on the left. Now from here we can state the null and alternative hypothesis. And I know it's been a little while since we've done this. We did it for the baby study, whether the babies choose the friendly toy or not. And so that's when we got to write and explore what it meant to say the null hypothesis and the alternative hypothesis. But the null hypothesis is that people are always doing things by random chance, so they're guessing. And the alternative hypothesis is usually the researcher's conjecture. So one thing I just realized we forgot to put in the symbol here. It says indicate the appropriate symbol. So the appropriate symbol, last time when we were studying section 6.3 and 6.4, I talked about the parameters for the different variables, categorical versus quantitative. So here the parameter is, the symbol will be P, the lowercase letter P, or the Greek letter pi. So let's write that in. All right, so P or pi. Now state the null hypothesis. Like I was saying, the null hypothesis is the by chance model. So we're going to say that the null hypothesis is students are choosing the name Tim at random. So you're just guessing. You took the survey, you looked at the two pictures, and you just guessed a name without really doing the facial prototyping. And so what does that look like in symbols? And so in symbols, we're going to say H subscript 0, so that's the null. Sometimes that's read H null. So null, the capital H is for hypothesis and the letter 0 for null. So this reads null hypothesis is that P, the parameter, is equal to 0.5. If people, why is it 0.5? Because if you're choosing at random out of two choices, the likelihood is, the probability that you're going to choose Tim is 0.5, right? 1 out of 2. And so now what about the alternative hypothesis? Now the null hypothesis is you're just guessing. Students are just guessing. But the alternative hypothesis will be they're not just guessing and there's something going on. The conjecture is that people use facial prototyping to assign a name to a face. So we're going to say the alternative hypothesis then students use facial prototyping and choose the name Tim for the image on the left more often. And so in symbols, we're going to say kind of similar to here, but it's going to be HA for alternative hypotheses. And what is it going to be? P is going to be not equal to 0.5, but here it says, so if you're not just guessing, if you're actually using facial prototyping, what do you expect the probability to be that you choose the name Tim? Is it going to be higher than 1/2 or lower than 1/2? Higher, right? If you're using facial prototyping, then you're likely going to choose the name Tim then more often, so the probability will be greater than 1/2. So then we're going to say that in symbols, H subscript A will be P is greater than 0.5. So those are our hypotheses. And so now we are going to look at the data. So now that I looked at your surveys, 18 people have taken it so far. I wanted to make sure that I recorded the video before too much time went on. So 14 students from STAT 300 assigned the name Tim, out of 18, assigned the name Tim to the image on the left. So let's calculate the observed statistic relevant for this study, and let's use the appropriate symbol. Now, this is a statistic because we're talking about a sample. Right here, we're using P because we're talking about the parameter, looking at the population, the entire set of 300 students. And now here, my data collected is just for the 18 of you that have taken the survey so far. So this is a sample, right? A small set of all 300 students. So what is our symbol for a statistic? And when I'm looking at a proportion, right, we're looking at the proportion. So can you remember what the symbol is? Yeah, for a sample, we use p hat. So in this case, we're going to have p hat is equal to 14 out of 18, which when you put that on a calculator, you get approximately 0.777 and a repeat. So I'm going to round to 2 decimal places and say 0.78. And now we're going to go do a simulation. So we're going to use the one proportion applet to simulate 10,000 repetitions, assuming the null hypothesis. So anytime that we do any sort of hypothesis testing, we're always assuming that things are happening by chance, and we're trying to see the significance towards it or against it. So can we prove that things are happening by chance, or do we have evidence against the fact that things are happening by chance? So we're always looking at the null hypothesis to see how much evidence we have that that's what's happening. So in this case, the null hypothesis is people are just guessing. So they're just assigning the name Tim to the image on the left at random, right? Not with any particular, in this case, we want to know facial prototyping. So our null hypothesis is people are assigning the name Tim to the image on the left at random without any special knowledge or consideration. So let's fill in this table. What does a success mean? So a success will be selecting the name Tim for the image on the left. The chance of success, this is the probability that we select the name Tim. So it's Tim or Bob, right? So then the probability is 0.5, 1 out of 2. And what is a failure? What would you then consider a failure? Because we recognize that this is binomial, so a success is selecting the name Tim. So a failure, then we would say it will be not selecting the name Tim. And so the reason that I'm going for the complement is because what if instead there were 3 pictures and I asked you to select the name for the image in the middle? Then there will be 1 out of 3, right? And so it will be, success will be selecting the name Tim for the image in the middle. But then how do you say the failure? So the failure, instead of saying selecting the name Bob, or if there were 3 pictures, there will be a 3rd name, we will just say not selecting the name Tim for the image in the middle. So that doing the complement rather than listing what the other option is better, right? So like in this case, failure, we could say selecting the name Bob for the image on the left. And that still says the same thing, but my point is that if you had more options, right? So if you had 4 names to choose from, it's easier to say success is selecting the name Tim for the image on the left, and then failure is not selecting the name Tim, so the complement of the success. And the chance of failure, because there are only 2 things in this case, it will still be 0.5. So I'm going to use the binomial notation. So success is P, probability of success is 0.5. Q is failure, the probability of failure is 0.5 as well. And that's because we have 2 names. So Tim or Bob, so the probability of choosing Tim is 1 out of 2. The probability of not choosing Tim is selecting Bob, which is still 1 out of 2, so 0.5. 1 repetition, it will be the number of students that we're using. So it will be 18 students. All right, so now let's go to our simulations. So use the one proportion applet to simulate 10,000 of these surveys. So essentially 18 of you completed the survey, and our data was 14 out of 18 students selected the name Tim for the image on the left. which is 0.78, so 78%. So we want to see how likely is that to happen. How likely, if I repeat this experiment, how likely is it that I get a similar result? And remember, we're assuming that things are happening by chance. So we're going to assume that students are choosing the name Tim for the image on the left at random. So no special considerations going and choosing the name, you're just choosing it at random. So let's go into the one proportion applet and find that out. By the way, before I open it up, I wanted to show you on your course modules, I added a new module, statistical analysis tools. So I put a link to StatCrunch, a link to StatDisk, a link to the applet we're about to use, the one proportion applet. I added the Z-scores PDF file for the negative Z-scores, and I added a positive Z-scores file also, so that you don't have to keep going to your book every time. When you're logged into Canvas, if you're in the modules page, you can always just access your Z-scores right away. So let's go back to our notes, and well, I guess since we're here, let's just use the link that is right there. So open the one proportion applet, and I don't like how this looks, so let's open it in a new window. There we go. So probability is still 0.5, right? And the one proportion applet essentially uses a coin to simulate our scenario. So heads is success. I wish it said probability or success instead of probability or heads, but essentially in this applet, heads is considered a success and tails is considered a failure. So for our purposes, choosing Tim is heads, right? That's our success. Number of tosses, it will be how many people did the survey. There were 18. And then number of repetitions is how many are we going to do? We want to do 10,000. If I leave it at 1, this is essentially going to simulate the 18 of you taking the survey. And right now it's taken a little long because I have show animation selected. When you unclick that, things will move a lot faster. So this is, notice that the number of heads, it says 13 out of 18. Number of tails is 5. And it gave me a little dot. So this will be exactly what I did by sending you that survey. So there's 18 of you took the survey. And this is what it gives me. The proportion then will be 13 successes out of 18. Now we want to do 10,000 repetitions. So I'm going to go to 1,000 first and click on draw samples. Notice that my show animation is unclicked, and that's why it went a lot faster. And so let me hide coins. So when you see this, this is just giving you the latest coin flip. So for the 1,000th repetition. So I'm just going to hide the coins because I don't need to see them. And notice that this is essentially now with 1,000 repetitions. So essentially if I went to 18 students 1,000 times and asked them, different students obviously, different classes, and asked them to assign a name to the image on the left, and then this will be the repeated results. And so now let's go to, I have 1,000 and we said we want 10,000. So let's put 9,000 for there for number of repetitions and draw samples. And notice that somewhere in here it should tell you that you have 10,000. Oh, right there. We have 10,000 total repetitions, and here is our binomial or distribution of our simulation. So where is it centered at? What is the shape? Where is it centered at? What's the variability? So it appears to be bell shape, so normal. And where would you say it's centered? Centered right around 9, 8, right? And does that make sense? So let's go back to the notes. Identify the shape, center, and spread or variability of the null distribution. So the null distribution is what we just created based on our simulation. That was our null distribution. So going back to it, this is our null distribution, meaning that we're testing if people are just choosing the name Tim at random for the image on the left, then this, when I repeat that survey, and I hand out that survey 10,000 times, this will be my results of that survey. So it appears to be normally distributed with the center around 8 or 9. Let's say 8.5. So we got the shape as bell shape, normal distribution, center. And so let's look at this. Because this is keeping track of the number of successes, it's a little bit hard to see, which we're saying 8 or 9, but we really want to look at the proportion. This is a binomial. We started with a binomial distribution, and now we have the null distribution. So now notice where it's centered at. It's centered around 0.5, which makes sense because we said the probability should be around 1/2. And so notice that if you click here, summary stats, it gives you the mean and the standard deviation. Yours may be a little bit different than mine because, again, we're doing a different simulation. It's kind of like a number generator. When we did that number generator last week, right, everyone got different numbers. And so this is doing the same thing. We're generating 10,000 replications of that survey, but it's like you going to 18 different students 10,000 times and versus me going to a different set of 18 groups of students 10,000 times, right? And so our results are going to be slightly different, but they should still be really, really close because the number of repetitions is so high. So my mean is 0.498. You may have something like 0.501 or 0.502. The idea is that it's really close to 0.5. And the standard deviation is 0.118. So now we're looking at the proportion of successes, which is what we want instead of the number of successes. So make sure that your proportion of successes is clicked. Now let's go back to the notes and put that in. So the center at around 0.5 for the proportion of successes, which means assigning the name Tim to the image on the left. And then with standard deviation of, what was it? 0.118 is what I got. Again, yours may be a little bit different, but close. So 0.118. So this is for the null distribution. Explain why the value of the center makes sense for this simulation. Why does the value of 0.5 make sense? It makes sense because we are saying, right, when we do the simulation, we're assuming the null hypothesis, meaning that things are happening by random chance. So if things are happening by random chance, people are assigning the name Tim to the image on the left at random, we expect the proportion to be about 0.5. So around 9 students will, right, half of 18 will assign Tim to the image on the left. So that's why that makes sense. So let's write that down. Now, one thing that if you're doing a problem like this and you want to show what the null distribution was, you can go to the applet, and on that image, you can right-click on it and do copy image, and then go back to your notes and you can insert the image there. So notice that, because then you will have the mean and the standard deviation of the null distribution. And the reason that we want the mean and standard deviation is because now we can answer questions about it, like how likely is it that we're going to get our statistic? Because now I can, using this mean and the standard deviation, we can find z-scores. So let's try the next, which is the next step, the strength of evidence, finding the standardized statistic. So calculate the approximate standardized statistic for our study. So this is really the z-score. So our observed statistic minus the hypothesized parameter divided by the standard deviation of the null distribution is going to give us our z-score. Now, our observed statistic is the number of students from the survey that assigned the name Tim to the image on the left. So going back to our results, we have that 14 students out of 18 assigned the name Tim to the image on the left. So that is our observed statistic. That is our p hat, 14 out of 18. So essentially, our z-score is p hat minus p divided by the standard deviation. So what was our p hat? We just wrote it up here. Our p hat was 0.78, our statistic, right? 14 out of 18. So 0.78 minus our hypothesized parameter, which is 1/2, divided by the standard deviation of the null distribution. The standard deviation of our null distribution is this, the 0.118. And again, yours may be a little different, so our z-scores may be slightly different. And then when we do that on our calculator, we get 2.37 is what I got. So your z-score should be pretty close to that value. The key idea here is observations that fall more than 2 or 3 standard deviations from the hypothesized value of the parameter can be considered in the tail of the distribution. And as we've seen before, right, if you're more than 2 standard deviations, you're considered significantly high, which means not likely to occur, low probability of occurring. So here, this is definitely more than 2. So we can say this is going to be or 14 out of 18 is a significantly high value to get. So according to this criteria, is the observed value of the sample proportion surprising when a null hypothesis is true? So meaning, when a null hypothesis is true, that we're assigning the name Tim to the image on the left just at random without any special considerations, is it surprising to get 14 out of 18 people choosing the name Tim? Yes, right, we will be surprising. If people assign the name Tim at random, we should expect about 9 students, so half of the students, to choose the name Tim. So this is very surprising. 14 is very far from 9. So what can we say? So then this means that we don't really have enough evidence, or rather we have strong evidence that against the null hypotheses that people are choosing at random the name Tim. So one of the things we can say then is that because our z-score is 2.37, right, which is more than 2 standard deviations from the mean, which means it's a highly unlikely value to occur, we can say that we have strong evidence that the null hypothesis is not true. So people are not choosing at random. So that means that there's something else going on. Now, saying that we have strong evidence that the null hypothesis is not true, right, that people are not choosing the name Tim at random, one of the important aspects here is to recognize that that doesn't mean that the alternative hypothesis is true. So saying that the people are not choosing at random, right, we have strong evidence that suggests that people are not choosing the name Tim at random. That doesn't say people are using facial prototyping. In terms of probability, what we can say is that because people are not choosing at random, it is more likely that people are using facial prototyping. But the big thing here, big idea is that just because we say the null hypothesis is not happening, that doesn't mean that facial prototyping is happening. That just means there's something else. There could be other things what we call confounding variables that are making you think that way, right? That are making you choose the name Tim for the image on the left. And you can kind of think about this in this day and age of online learning and taking online classes. When you enrolled, for example, even in my class, you probably saw the name Owens and So my question to you is, did you have an idea of what I was going to look like based on the name? And so that is our subconscious, like whatever's going on in our mind that makes us assign a picture to the person. And then once you see whether the profile picture or welcome video or something, you're like, oh, that is not what I was expecting the person to look like. And you move on, right? So it's not, but there's something in our subconscious. It could be facial prototyping that is making us assign a picture to a name or a name to a picture. And so that's sort of what's happening here, right? And oftentimes even people are sometimes they're like, oh, you don't look like an Owens, or oh, you don't look, and it's like because there's something going on there. It could be facial prototyping, it could be something else. So in step 5 here, that's essentially what you would say. Write a paragraph that if to a member of your family who has not taken statistics, summarizing the conclusion here. So what did we do? What was the whole study, and what's the final conclusion? So what I just said, right, that we have strong evidence against the null hypothesis, so people are not choosing the name Tim at random. And then what else could be happening? And now here, since we know our z-score, you can go back to the z-score table and see the probability that our value 14 out of 18 would happen. So you can go and look at that area. So because our z-score is positive, we are going to look at the positive z-score table, and so we're looking at 2.37. So I'm going to go over here to 2.3, 2.3 and then 7. So 2.30, 1, 2, 3, 4, 5, 6, 7. So 0.9911. Now notice that the picture is giving us the area to the left, and we want the probability that z is more than. So we will have to do 1 minus, what was it? 0.9911. So essentially, if I wanted to find the probability here that our x, right, is greater than 14, greater than or equal to, I will have to say this is the same thing as saying the probability that z is greater than 2.37. Why greater than? Because remember, alternative hypotheses, which was up here, said that our alternative is that the proportion is greater than 1/2. So we want to see what is the probability of things are more than that, like that we get the likelihood of getting a value 14 or more. So then I'm going to go over here and say that is, now remember our z-score gives us the probability that the x is less than z. So to do the probability that x is greater than z, I have to do 1 minus that value. So let's go back to our notes here. So this is 1 minus the probability that z is less than 2.37. And the reason that we do the less than is because that's what the table gives us. The table gives us the less than area. So this will be 1 minus, what did we say it was? 0.9911, I believe. So that will be our probability. So do that on your calculator, which is approximately 0.0089. So we can say, rounding to 2 decimal places, I'm going to say this is approximately 0.01. And now notice that if we go back to the applet and I put in here as extreme as our statistic, so our statistic was 0.78, because now I'm looking at proportion of heads and do count. Notice that is 0.01. So that is our probability of a statistic as extreme as ours, right? What our survey said, 14 out of 18 students chose the name Tim. So the likelihood that as we repeat this over and over and over is 0.1 probability that this is going to happen. So not very likely, right? notice here it gives us the number 141. So essentially this is saying that 141 surveys out of 10,000 had a result as extreme as our survey. So not very many, right? In 10,000 repetitions to only get 141, that's not very likely. So that also gives us strong evidence that the null hypothesis is not true. So things are not happening at random. You can also do it by going to StatCrunch and doing the normal distribution as we did last time. And in the normal distribution, you would put in, right, your 0.5 as the mean and 0.118 as the standard deviation, and your x will be the 0.78. Or you could do it with the numbers. You can say the mean is 9. The only problem is that we wouldn't have necessarily the standard deviation because we had no data given to us. That's why we had to create the null distribution. Now, when we don't want to do things with the simulation, that's when the binomial, the normal approximation to the binomial comes in handy, because we can say, in order to approximate with a normal distribution, we want NP to be greater than 5 and NQ to be greater than 5. Now, in our case, the Bob and Tim study is a binomial. Yes, right, it has a fixed number of trials. We had 18 students take the survey, so that's a fixed number. Each trial was independent, so you taking the survey and selecting whichever name you selected did not affect another student from making their selection. So they're independent. Trials are each classified into 2 categories. So we had Bob or Tim, and success or failure. Assigning the name Tim was the success. Trials with the property that the probability of success remains constant, right? Each of you had to choose between the name Tim or Bob. So each probability is 1/2. So that was the same for everybody. So our Bob and Tim study classifies as a binomial probability. So now, if it is binomial and it can be approximated with a normal distribution, this has to happen. NP is greater than 5 and NQ is greater than 5. When that happens, then we can say the mean is N times P and the standard deviation is NPQ. So when this criteria is satisfied, then we don't have to use a simulation, right? So notice that here, I didn't have, going back to our data, I don't have anything given to me. I don't have the mean of the population. I don't have the standard deviation of the population. So I really can't do much with it. In going to the bottom, if this is satisfied, now I can say, oh, the mean is NP and the standard deviation is NPQ. And with this information, now I can find the z-score for my own proportion for the statistic, right? The 14 out of 18. I can put that mean here and that standard deviation here. And then I don't have to do the simulation. But when this isn't satisfied, that's when we do have to do a simulation. So try it for the Bob and Tim. What you'll find out is that it does not qualify. So you have to use the simulation. But for this example, our P is 29.2. And so Q will be 100 minus that, or change it to a decimal. So 0.292 is P. So Q will be 1 minus that. And now we could find N times P, and you'll see that it will be greater than 5, and N times Q should also be greater than 5 for this example because the number is 1480. So try this on your own. And then, assuming that this is correct, find the probability that 455 or more adults sleepwalked. So essentially you'll be doing what we did here, finding the z-score and finding the probability by looking up the tables. But the nice thing is that now you don't have to do a simulation because you are going to be able to find your mean and your standard deviation based on these formulas, your NP and your square root of NPQ. So when this highlighted condition is satisfied, we don't have to use a simulation. We can just use the mean and standard deviation given by these formulas. Okay, try this on your own. I'll record another video going over this problem, but I want you to try it on your own first and before you watch that next video.